All right, so let's get started. A few reminder items here. So for the classroom surface disinfection, today is Jera and Alyssa. Okay. Um, so because of power outage yesterday, and then a couple of you guys actually requested, I didn't say yes, but um, so I actually just extended okay, last night at some point, I think. So you have 1 day extension on your homework. It's not due until Friday, okay? Um, exam one should be still in next week at some point, okay? um, just a reminder, again, lab report is due 5 days after your lab activities, okay? So if let's say if you are having your lab on Wednesday, then it's due on next Monday, okay? And if you have your lab on Friday, then it's due Wednesday the next week, okay? All right. So that's on that. So last time we talked about motions in 2 dimensions. So basically you are going to break your 2-dimensional motion in X and Y component, okay? So then if there's acceleration, then you change the terms in the 1-dimensional equation of motions, the acceleration into the acceleration in X component and Y component. Okay, so basically you are just changing that. Then you are going to do the motions just twice, the 1-dimensional motion just twice. Okay, and we mentioned about a particular 2-dimensional motion as projectile motion. So in that case, your X direction acceleration is 0. Your Y direction acceleration is negative of G. Okay, G is the constant of 9.80. So if it's negative of G, that means you are picking the upward to be positive direction in the vertical direction. Okay, so then the equation motions, the one we saw in the previous slide. So again, you are replacing the AX just with 0 and then AY with minus G. Okay. Um, so this is the projectile motion. And I think we didn't get a chance to do the exercise or the example, but let me go back one slide over here, okay? So in these 2 sets of equations, you'll notice that most of quantities are different from each other, but one quantity, okay? So in the X direction and in the Y direction, the equations, they have one common quantity, which is T, time T, right? So that's one common quantity. Otherwise, the rest, they are different, okay? They are the X component of position, X component of the velocity, and X component of acceleration in the X direction, and then Y component of everything, again, in the Y component, okay? But the common quantity here is T. So that means T will be the same for the motion for the during the time that the object is in motion. Okay, so so then the T, if you cannot, so in this way, if you are looking for T, if you are checking on your equations in X direction, if you couldn't find T, then you probably would turn to the equations in Y direction. Okay, so that's one thing you want to practice when you are looking for T and then couldn't figure out in 1 dimension, but then you look at it in the 2nd dimension, okay? All right, so let's take a look on the example here. So this one says a second baseman tosses the ball to the first baseman who catches it at the same level from which it was thrown. The throw is made with an initial speed of 18.0 meters per second at an angle of 37.5 above the horizontal. It's asking you the following questions. What's the horizontal component of velocity just before it's caught, okay? And then how far has the ball traveled horizontally? How high does the ball go vertically before it starts to descend, okay? So those 3 questions. If you guys got a chance to work on this earlier, you can submit your answer, okay? Otherwise, you can just get started. I think we'll be looking at the solution together just in a couple of minutes. Okay, so go ahead and then read the problems and then see how you would like to solve it. All right. I think I'm gonna to check the solutions with you guys together now. Okay, so let me see if there's anybody have the answers submitted. Okay, looks like a couple of you guys have done that. Okay, so if you didn't start this before the class, it may take quite some time. Okay, so we'll just look at the solution together now. Let me bring up the camera. Okay. So A is asking what would be the horizontal component of velocity before it's caught. Okay. So in this case, so if you look at the equation of motions for the horizontal component, the velocity in x is going to be just equal to its initial velocity. Okay, initial component. And then the initial component will be V0 cosine of the angle. We are given the angle. So let me just do the sketch here. Okay, it's been, I'm going to take the original position of the ball as the origin. Okay, so it's been thrown by the second baseman in that direction. It tells us V0, its magnitude is 18.0. Okay, and then this angle with horizontal is 37.5 degrees. So then after it's thrown, the ball is in the air, it's the projectile motion. Okay, so then we also know that the AX acceleration in X direction is 0. The AY would be, if we take upward to be the Y positive, then the AY will be minus G on minus 9.80 meters per second square. Okay. So it will fly in the air and then be caught by the first base, by the second baseman. Okay, baseman here. All right. So on the first one, you just plug in the two numbers there, 18.0 meters per second, cosine of the 37.5 degrees for the angle. Okay. So you'll get 14.28 roughly meters per second, or if you keep 3 sig figs as the quantities given, then it's 14.3 meters per second. Okay, so it be pretty straightforward here. So we can see what else we are already know about the problem here. Okay, so if you pick the origin to be at the initial position, then you also assume that its original x is 0, original y is also 0. Okay, so we actually have 6 pieces of information over here. So 1, 2, 3, 4, 5, 6. Okay, and then also for this, the final y, because it's being caught at the same level, so final y then will be equal to initial y, will be also 0. Okay, so I think 7 pieces of information are available here. All right. Although it looks like in the problem it only gives gave you 2 numbers, okay, but in fact you can get a lot of more information on top of those 2. Okay. Now the second part, if you are looking at your PowerPoint slide, it's asking you where in X is this ball being caught. Okay, so you're looking for X in the second part. Okay, so basically that's what's asking in the problem here. All right. So you are looking for X. All right. You look at the equation of motions in X direction. So the ones it has X. So there's this one has X. V initial Z X times T, right? Normally you would have another term that has oscillation, but AX is 0, so that term doesn't exist here. Okay. So this might be the equation you'll be looking at. So you're looking for your final X, your initial is 0. Okay, you know that. And then this guy, you know this. Okay, it's the 14.28. All right, but you do not know T. Okay. So again, if you look at the rest of equations in X direction, you probably wouldn't figure out T. Okay, so that's why what I told you earlier, if you couldn't figure T in one dimension, then you turn to the other dimension. Okay, So then we'll be looking at y dimension here. So in y dimension on the equation of motions, and you'll be checking on those equation of motions, and you probably will figure that you can use this equation to figure out your t, okay? Y equal to y0 plus v0y times t minus 1/2 gt squared, okay? Because in this equation, you have your final y and initial y, your initial v0y, okay? Initial velocity in y component, you can figure that out by doing the v0 sine of the theta, because v0 is given, theta is also given, so you can figure that out, okay? So g is in the 9.8, then the only unknown is the t in the equation, okay? So you can solve for your t there, and then plug the t back into this equation, okay, to figure out your x, all right? So that's what you are going to do. Let me see. So you can figure out your v0y first, okay? You can plug in the numbers here, 18.0 meters per second times sine of 37.5 degrees, okay? So that tells you your v initial velocity in y component. Did I do this somewhere? I guess I didn't do it this way over here, but you guys can plug in those two numbers in your calculator and then figure it out easily, okay? It actually turned out you don't have to do that. But let's take a look here. Now you have this is 0 at for your y final, and the initial is 0. So plus v0y times t minus 1/2 gt squared, okay? So before you plug in numbers into your equation, you can actually inspect the terms you have here. So you figure there's this t here, there's this t squared. So you can pretty much divide everything by t, okay? So the zeros divided by t will be still 0, okay? So this one divided by t, we'll get rid of the t here. And then this one divided by t, we'll get rid of the square, okay, with only t there, okay? So then pretty much this is telling you that 0 equals to, so this one is 0, you don't look at that one, v0y minus 1/2 gt, okay? So in this case, okay, I know you guys, a lot of times you guys prefer to just plug in numbers and solve for the t here, but oftentimes I will do the other way around, because it will turn out that you can plug in your numbers at the end when you have the expression for the x, okay? So you can do that way. So I'm not going to just show you how to do it that way, but you guys can still do the way you prefer, okay? You can plug in the numbers here, like solve for this one first, and then solve for t first, and then plug in t back over there, okay? As I say, I'm going to do this differently. So from here, I can know that if I solve for t, okay, a couple of steps of algebra here. So let me see. Let me do it this way, okay? So if this minus this gives you zeros, that tells you these two are equal to each other, okay? Because only the same numbers, if you are subtracting one from the other, then it will give you 0. So that tells you those two are equal to each other. Now multiply both sides by 2 to get rid of 1/2, okay? And then divide both sides by g over there to get rid of g here. So then your t is equal to that. So t is equal to twice of v0y over g, which the v0y is twice of v0 sine of theta, okay, over g. Okay, so this is my expression for t. I'm doing this way so that if you know the expression for t, then because this is universal, right? It doesn't depend on what's your v0 and your theta, because then this applies to whatever v0 is given and then theta number is given. Okay, so this is general formula here then for projectile motion, like this one here. Okay, but it only applies when the initial position and then final position in y direction that are at the same level. Okay, so that does have one condition here. Okay, So the y should be equal to y0. Okay, those two should be the same. Then the t is equal to that. Okay, so this applies when y equals to y0. Okay. All right, now I have this one. Then I can solve for my t or my x. So my x is equal to v0x. Okay, the x component v0x, which is v0 cosine theta. Okay, so I'm going to just replace v0 with that guy, v0 cosine theta. Okay, multiply by my t, which is this expression 2v0 sine theta over g. Okay, so then I'll get 2 here, I'll get v0 and v0, so that means v0 squared. So v0 squared times 2 times a sine theta, and then times a cosine theta divided by g. Okay, I can rearrange my terms because they are you are doing multiplication of them. Okay, all right, so then I will be looking at this one here, this expression over here, twice of sine theta times cosine theta. Okay, so if you are very good at trigonometry, you will realize that if this is the 2 sine of theta and cosine theta, then it should be so 2 sine theta times cosine theta, that should equal to sine of 2 theta. Okay, so then you realize, okay, then this is v0 squared sine of twice of theta over g. Okay, so this is your x. So that's the x position when the ball is caught at the same level as its initial level there. So usually we will call this as the range of the projectile motion, okay, because that's the how far it has flown in the air. Okay, so that's this. So that's the range. Okay, so that's r. All right. So then this is the general expression for the range of a projectile motion if the object is being caught at the same vertical level. Okay. So in that case, you can see that without plugging any numbers, then you can get this expression. Now you can plug in your numbers and the final step over here. Okay, so then you do, let me see. So now you plug in your numbers here, 18.0 meters per second squared sine of 2 times 37.5 degrees, okay, divided by 9.80 meters per second squared. Then your range is equal to, okay, plug in the numbers, you'll get your range as 31.93 meters, okay, that's your range. Keep 3 sig fig, okay, then that's that. All right. Yeah, I think everything looks fine. Oh, actually, did I do right? Yeah, so that's fine. Or if you do the other way, as I told you, you plug in the numbers to figure out t first, okay? So I think I did calculate t at some point, just for your reference though. So if you calculate t first, this is 2.236 seconds, okay? And then once you plug that into this equation over here, so then x is equal to this 14.28 times 2.236, okay? All right, then you'll get the same number, okay? So either way, all right? So I just wanted to show you that what would be the general expression for the range, okay, of the projectile motion if it's caught at the same level, okay? Questions you guys might have? Okay. All right. Now let's look at part C here. So part C is asking you, how high does the ball go vertically before it actually turns direction? Let me see if I remember that correctly. How high does the ball go vertically before it starts to descend? Okay, so it goes up and then comes back down. So as we discussed previously on one-dimensional motion, so this happens here as well, okay? So in the horizontal direction, your velocity doesn't change, right? It's constant because your AX is 0. In the vertical direction, it actually goes up, right? The velocity goes up and then goes down, or the object goes up and goes down. In the horizontal direction, it keeps going to the horizontal, okay? But in the vertical direction, it goes up and goes down. That's how you get a trajectory of like this, okay? So vertical direction, the velocity decreases, and then at the high point of the flight, it actually goes to 0, okay? So at vertical, when the object is at the high point, the velocity is 0, okay? So then it's asking you what would be that y at this point, okay? All right. So if you are looking for y here, okay, you might, again, you'll be checking on the equation of motions in y direction. So you might figure out that this is the equation you want to use, similar to the one we just used earlier, okay? But now in this time, when the object is at a high point, it's exactly at half of its flight, okay? So it's at half of the flight because as we, for the lava bomb problem, if you guys remember, when it's at high, when it reaches the high point and then comes back, it takes exactly half of the time for the whole journey, okay? So this is the same here. So then let's say 1/2 here, t 1/2 over here, okay? So if you realize that, then t is 1/2 of what you had earlier, right? If you solve for t at some point over there, you can just take 1/2 of that number and then plug it into this equation, okay? And then you'll be getting your y, all right? Or you can do the other way around. You can figure out t a different way because you know that Vy is going to be 0. That's going to be equal to initial y minus gt, right? So then t is going to, so this guy is 0, and then this is initial y. So these two equal to each other. So then it's V0y over g, which is V0 sine theta over g. Okay, so either way, if you are doing this way, you also figure out it's going to be half of that. Okay, plug in numbers here, and then you'll figure out t to be half of that. Then you can put t into this equation. Okay. So your y0 is 0, so that one goes away. So you're looking for y here now. It's the v0y times t, this t here, which is 1/2 again, okay? So it's your v0y, which is v0 sine, okay? So I'm going to just take v0 sine here in the place of that, times the t, I can use that t, v0 sine theta over g, okay? Minus 1/2 g of this guy. But do remember the square, okay? So on the t term here, that's something people often forget. It's a square term, t square, okay? So if you do that, you'll see that this guy here, on the first term here, the v0 square, because you have two v0s, and then sine theta also you squared it because there are two sine thetas, g minus 1/2, okay? Here is the same v0 square sine square theta over g square, but you have a g there, okay? So you can see this g and this g will cancel out, all right? So it's this term, the first term minus 1/2 of itself, right? So the first term minus 1/2 of itself, then gives you 1/2 of it. Okay. Again, this is a general expression. Okay. But you guys can do the way you prefer. Okay. You can solve for t first and then plug in numbers. Okay. So so 1/2. Now I usually prefer to plug in numbers at the end. Okay. So whenever if I can recheck my derivation over here later, and then if I figure something is wrong, I can correct on my expression. Then I can just at the end, I will just plug in the numbers at just one time. Okay. So instead of if you are solving for t-half first, okay, then later on you figure, okay, your t-half wasn't right, then you will be plugging the numbers in your calculators all again, like multiple times, okay? So that's why I prefer to get my final expression first and then plug in the numbers, okay? So if I figure something wrong in between, then I just check on my numbers just one time, okay? But either way, will work. So 1.26 meters to keep 3 digits, okay, 6.13. All right. So that's my how high it goes before it turns direction. Okay. Any questions you guys might have?
Yeah, just to double check. So when you subtract the sort of the when you're at v 0 squared sine squared theta over g minus 1/2 of it, you're just subtracting half, so you're just getting half. Is that right?
Yeah. Yeah. So the question online is when I doing this, actually over here, this guy minus that guy. Okay. So do I just do like 1 minus 1/2? Okay, and then take the expression down. Yes. So the first thing is basically 1 times this a bunch of thing here, and then the second term is half of the bunch of this expression here. Okay, so basically 1 minus half, and then you have half remaining. Okay.
Thank you.
All right. Okay. So I know at this point, because this one, when we are doing this projectile motion, it's a two-dimensional motion. Okay, so things becomes more complicated. You are not just doing the one-dimensional problem twice, but you have to combine the two. Okay, in many cases you couldn't find one quantity from one direction and then you turn to the other direction. Okay, so I think the difficulty level kind of goes up 2 levels here. Okay, so if you are struggling right now, it's totally normal, okay? But you want to do a few practice problems like the ones in the homework, so then you are getting familiar with this type of problem, okay? All right, so let me see. I think I should be sharing my screen with online folks. All right, so as I derived in the previous problem, you can see that, so for projectile motion, if it ends at the same level as initially it is, okay, then the range is equal to the, so the range then is equal to V0 square over G times sine of 2 theta, or as I did, I was doing like V0 square sine 2 theta over G, okay, so they are the same, okay, but in order to apply this range equation, okay, so this is the condition that has to be satisfied, okay, initial and final elevation, they are the same, okay, so in many in many problems, when the object is initially launched, okay, at certain level, for example, if I throw something from the table level of the table and then it reaches on the ground over there, okay, So in that case, then you wouldn't apply this equation for the range because the two initial and final levels, they are different, okay? So just keep in mind, if you want to apply this equation, initial and final elevations, they should be equal to each other. All right, so with that range equation, you can see that then the range is going to be just determined by the initial velocity, the speed, and then the launch angle, okay? So if initial speed is fixed, okay, so that says if, for example, if you are kicking a ball, so you might just have a limit force that you can exert on the ball. So then this guy will be having a limit of fixed number, the initial velocity, right? So, but you can vary the angle to reach for your maximum range, okay? So the angle here, you can see sine of 2 theta here, does have a maximum, okay? For a sine function, it has a maximum of 1, right? So then you can change your angles to reach the maximum range, okay? So for you guys, if you are playing soccer, you want probably know the angle is going to be about 45 degree if the condition is perfect, no wind, no air resistance, okay? But in reality, it's not going to be 45, it's going to be around like 40 or 42 degrees, okay? And then you can reach your maximum range over there, okay? Yeah, because sine of 90 gives you the maximum of 1. So that means if 2 sine of 90, so that means 2 sine is equal to 90. That's how you get this 45 degree as the maximum range, okay? 1/2 of 90 is 45. Okay. Another thing about the projectile motion, as I mentioned, if the initial and then the final elevation, they are the same, so then at the high point of the flight, okay, so the time it takes will be half of the whole flight, okay? Again, it has to be initial and final position, they are in the same level, okay? And then also, the angle of the velocity, okay, with respect to horizontal angle, if they are at the same level, okay, so then theta on one side, and then you should have minus theta on the other side, okay, because the speed in the vertical direction is the same, but the direction of the velocity are opposite to each other, okay, so that's why you get theta and then negative theta on the other end, okay, when you are at the same height, because on one side is going up, on the other side is going down, okay. So that's the symmetric here. All right. We'll be looking at another example here. Okay, so then that will pretty much take occupy all the time we have for today. So this one says it's an archer shoots an arrow at a 75.0 meters distant target. The bull's eye of the target is at the same height as the release point of the arrow, okay? So in this case, then the arrow, initial and final elevation, they are the same, okay? It's asking you at what angle must the arrow be released to hit the bull's eye if the initial speed is given at 35.0 meters per second. And then if there's a large tree halfway between the archer and the target with an overhanging horizontal branch 3.5 meters above the release height of the arrow, will the arrow go over or under the branch? Again, I'll give you guys a couple of minutes to kind of digest the problem and then probably hatch a plan how you want to tackle it, okay? And then we can take a look on the solutions together. All right. So I'm going to check the solutions with you guys together. And then if we have sometimes remaining, we may be checking on some of the homework problems. Okay, but it looks like probably we are not going to have enough time for that. But we'll see about that. Okay. So on this one, it says the arrow is being launched initially with 35.0 meters per second as the speed given. And then I think it tells us that this guy, the bull's eye is at 75.0 meters away, okay, from the original. So if I set up the original position to be my origin, so then my initial position, x naught is 0, y naught is 0, okay? And then this guy is 75, all right? It also tells me that the target and the initial launch point, they are at the same level, okay? So that means y is also equal to 0, the same as the initial, right? Now, because the arrow is released in the air, so then we know it's a projectile motion. The x direction oscillation is going to be 0, and then the y direction oscillation is going to be 9.80 meters per second negative. Okay, so and then we are given this guy. Okay, so we are looking for theta initially. Okay, so if you are looking at the equation of motions, okay, so then for the x direction, it tells you x is equal to x naught plus v0x times t. All right, and then vx is equal to v0x. And then the third equation is the same as the second one, okay? So, and then y direction, y is equal to y0 plus v0y times t minus 1/2 gt squared. Vy is equal to v0y minus gt. And then the last equation will be vy equal to v0y squared minus 2g of y minus initial y, or delta y, okay, either way. So when you look at the equation of motions, you will see there's no information about angle theta, right? But in actually, the initial velocities, they can be expressed in terms of theta, right? So that's something we actually learned earlier, but we haven't actually get a chance to practice much or more problems. So, but this is what this guy is, okay? And then y is v0 sine theta, okay? So that's the velocity from the velocity vector is x component and y component, okay? Will be magnitude times cosine and then magnitude times sine. So then you actually kind of relate the angles into the equations, okay, by replacing the x component initial velocity and y component initial velocity in these two expressions, okay? So I think if we are just looking at this one, these two equations, it would be sufficient for us to solve for this problem, okay? I will check on that one. So x is equal to x naught plus v0 cosine times t, okay? So you're looking for sine, you're looking for theta here. You need to know this guy, and the t, right? But this is 0, this guy is 75. It's given, okay? And then this is 35. You need to know t, all right? T is not known, but once you figure out t, then you should be able to solve for your theta, okay? You solve for cosine theta first and then do inverse of cosine theta to give your theta, okay? So now we are looking for t then, indeed, if we want to look for theta. So then you look on the x direction equation of motions. The first one has t, the next two, they don't, okay? So you probably wouldn't figure out t from those equations. Then as I said, you will then turn to the second component, okay? So second direction here in y direction. All right, so the first one will have t in it. Then let's check on this one to see if you can figure out t there, okay? So y equals to y0 plus v0 y, which is v0 sine theta, okay? times t minus 1/2 gt squared. Okay, you kind of examine this equation here. These two are zeros. Y and y0 is 0. Okay, so then t here, you can kind of get rid of t as what we did earlier. You can divide both sides by t, each term by t, not t squared. So this one by t, this by t. So then it would be 0 equals to 0 over t will be still 0. V0 sine theta minus 1/2 gt. Okay, so you can rewrite the second equation here to become this equation. All right, now you'll be examining this equation again. You'll see this guy is given as 35. Okay, this is constant 9.8, but you still have theta and t. You still have two unknowns here. All right, so you probably couldn't solve for t directly. Now what do we do? In this one, you need t in order to solve for theta, right? So then we say we turn to the next direction here. So then we are hoping we can get we can solve for t, but here again we couldn't solve for pt because theta is again an unknown. Okay, but if you have two equations, one equation and then two equations, right? You have two equations, then you have two unknowns in there, right? So then you can actually solve for both of the unknowns. Two equations will give you two unknowns, okay? And which two unknowns will give you enough condition to solve for the two unknowns, okay? So the first one here is 75 equals to 35 cosine theta, okay? Times t, that's the first equation. Let me just rewrite here. The second equation is 0 equals to 35 sine theta, okay? Minus 1/2 9.8 times t, okay? So I have two equations, I have two unknowns to solve, right? So then I can probably solve for my unknowns, okay? So to do that, you can write one unknown in terms of the other unknown and then plug it into the other equation, okay? So say from this equation, you can write t in terms of theta, okay? So basically you will be dividing both sides by 35 cosine, okay? So then t is equal to 75 over 35 cosine theta, okay? So once I do that, I can take this guy into the second equation, the other equation, okay? And then I'll be solving for theta in that case. So then if I do this, 0 equals to 35 sine theta minus, so 1/2 of 9.8 gives me 4.9, okay? 4.9 times 75 over 35 cosine theta, okay? So then this guy equal to that guy because this guy minus that guy equal to 0, okay? So you can set up the two terms to be equal to each other. 35 sine minus 4.9 times 75 over 35 cosine, all these two equal to each other, okay? All right, now you can do multiply both sides by 35 cosine, multiply by 35 cosine, okay? Then this is 35 square sine theta and cosine theta, okay? Equals to this number. Now you need to do the trick here because sine of theta times cosine theta, as we did in the previous problem there, when we were looking for a range, okay? Cosine times sine will be, or multiplied by 2 will be sine of 2 theta, or the other way around. If you do this guy will be equal to 1/2 of sine 2 theta, okay? So then we are going to say this is then 35 square multiplied by 1/2 of sine 2 theta equals to this guy multiplied by 75, okay? Now you can solve for sine of 2 theta. So sine of 2 theta then is equal to all this number 4.9 multiplied by 75 divided by 1/2 times 35 square, okay? So then you can plug in the numbers into your equation, and then it will give you a number. Okay. Then you do sine inverse of sine 2 theta on both sides of equation. Okay, that gives you 2 sine on the left hand side. Okay, equal to a certain angle. Let me see what will be the angle. That angle looks like 36.87. So all this number you plug them in, it be about 0.6. Okay, then it's the angle. So then theta is equal to half of this number. Okay, so 18.4 roughly. That's the number you'll be getting. Okay, so this is one way of doing it. Okay, you can do it this way. As I said in the previous problem, you can solve for one thing and then plug it into the other thing. Okay, but because when we solve for the previous one, we know that range is equal to, or the x range of x is equal to, the final x is equal to v0 square sine 2 theta over g, right? Then this XR range, that is 75, equals to 35 square sine of 2 theta over 9.8, right? So then I can directly solve for my sine 2 theta, okay? So my sine 2 theta over here, you multiply both sides by 9.8, get rid of that, okay? And then divide both sides by 35 square, get rid of this. Okay, so your sine 2 theta then is equal to 9.8 multiplied by 75 divided by 35 square. Okay, this would be again 0.6 roughly. Then you do sine inverse of sine 2 theta on this side, and then on this side sine inverse of 0.60. Okay, so on the left hand side, sine inverse of sine will give you 2 theta. Okay, so for trigonometry, this is something like if you are doing plus and minus, right? So then get rid of it. Okay, so this again is 36.87. That tells you your angle is 18.4 degrees. Okay, roughly. So that's why we spent quite some time on derive the range equation in the previous problem. Okay, so that means you can apply it directly here. Okay, without doing it again. Okay. Any questions you guys might have on this one? RA here.
Can you show the back again, please? I just needed to see where you did some of the algebra at the end.
This guy. The other way of doing it.
Yes.
Okay. Hopefully it will capture it, and then you guys can review it on the video that I will post later. Okay. I think it catches the whole page here. Okay, so this is A. B is asking you, let's see. It's asking you if there's a tree halfway in between the archer and the target with an overhanging of a branch 3.5 meters above. Will the arrow go over or under? Okay. Yeah, it looks like we don't even have problem for this part. Okay, so we don't have even time for this part. We'll come back on Friday on this part then. Okay, so but if you guys have time in between, you can check on this one by yourself. Okay, and then we can look at the solution together on Friday. Okay. All right, so we will have lab this afternoon on vectors. So if you guys get a chance, you can read the manual before. Okay. So a lot of times for the everything you would need for the lab report, you can actually read through the lab manual. It's all given, the instruction is all given how to complete and then how to do the data analysis. Okay, so yeah, so That's also another thing I think I didn't mention, but everything you need is in the lab manual. Okay. Of course, you guys can still ask me when you guys have any questions. Okay. All right. I'll see you guys in the afternoon, and then also the rest of the class in the on Friday. Bye, guys.